Hello, scientists. So this is part 2 of Lab 5.06 on masses and springs. We're going to be looking at harmonic motion, which is the idea that something repeats the same motion over and over again. We already looked at pendulums, and now we're going to look at springs because they have the same up and down motion, just not back and forth. So it says here in the directions that we should remove friction using the button on the right. We'll look for this little green slider and move it all the way to the left so that there's no friction in the system. And so our spring will just keep going up and down, and none of the energy will be converted to heat, and so it can all stay in the bouncing. We're going to activate the stopwatch, which looks like this. We're going to get the 50-gram mass bouncing, that's the smallest mass, on the left spring and record the time it takes for 60 cycles. So just like you understand a period in a pendulum, a period in a spring or a cycle in a spring is all the way down and back up. So we're going to count 1, 2, 3, 4, etc. up to 30. Time that and then divide by 30 to get the time for just one bounce. So let's go into the simulation and figure it out. So remember, we were going to switch the friction to none. We're going to look at spring 1 here. We can look at the energy. It's not going to be an important part of what we're doing. We're going to make sure we're on Earth for the first for table 4. And we want the stopwatch to run here. We don't need the ruler, we can just kind of leave that where it is. You may want to move the timer here so that it's out of the way. So I'm going to hit start on the timer, and then I'm going to count 30 bounces. And we're going to time for 30 bounces, and then you can do this for the other ones. Oh, I forgot to hit the timer here. Three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so you notice in the real life, a real spring, if you set it bouncing like this, is eventually going to stop because there's friction in the system. In real life, there's always friction. Here, the spring doesn't stop because there's no friction. If we turn up the friction here, eventually the spring will come to a stop because some of the kinetic energy or potential elastic energy or potential gravitational energy is getting turned into heat. So now we have our time for 30 bounces with 100 grams. And let's go back to our data table. Hello, we are back from the sim, and I accidentally put on the 100-gram mass, but that's okay. You can do the 50-gram mass and the 250-gram mass, which is the same thing as 0.25 kilograms. And 0.05 kilograms. Since I did 0.1 kilograms, we'll figure out the period for 0.1 kilograms, which is just the total time divided by 30. So there's what it is on my calculator, 0.61 seconds. 0.61 seconds. And the units are already nicely there for you. So now you can go pause the video and do the 50-gram mass and the 250-gram mass. Just remember to count the bounces. We're going to repeat the exact same experiment on Jupiter. So remember, when you go to a different planet, there's a different force of gravity. There's a different acceleration due to the gravitational force of that planet because there are different masses at different planets. So let's go see how our spring, our same spring, bounces on the planet Jupiter, which is one good thing you can do in a simulation, because generally you can't go to Jupiter to do your science experiments. So we're going to do pretty much exactly the same thing we did for the last experiment, except this time I'm going to look at what would happen if we were on Jupiter, or the force of gravity is a little bit different. So I'm going to pull the spring up here. Oh, I better reset my stopwatch first. I'll reset that. I'm going to let this, oh, we still have to have friction on 0. So remember, because we want all of the variables in an experiment to be the same. We want the same spring, we want the same amount of friction, we just want to go to a different planet. So I'll get this bouncing and we'll count the time for 30 cycles or 30 periods. 3, 4, 5, 6, 7, 9, 10, 11, 17, 18, 19, 20, 21, 22, 24, 25, 26, 27, 28, 29, 30. Yeah. Here, let's turn up the friction. Let's turn it back to reality here so it stops bouncing. So now we have to go and do exactly the same thing. We just did take this total time and divide it by 30. So we went to Jupiter, we counted the time for 30 bounces, that's 19.02, or maybe if you got a different time, you could put that time down. And we divided this number by 30 to get the period of 1 bounce, or the time for 1 bounce, of 0.63 seconds. So it's up to you to pause the video and repeat that procedure for the 50-gram mass or the 0.05 kilogram mass. That's the smallest one, and the 250-gram mass, which is also 0.25 kilograms. So repeat the experiment on Jupiter. So pause me and go do the Jupiter experiment now. All right, you're back. Now it's our job to work with the red, green, and yellow masses that we don't know the exact mass for, and use the formula for a spring's period to determine the unknown mass. I have rearranged this formula here for you so that we get mass is equal to K, the spring constant, times T, the time for 1 bounce, the period, divided by 2 pi, and you square everything in the parentheses. And I'll show you how to do that math in just a moment. Right now, let's go to the simulation and let's count the time for 30 bounces with the yellow mass on spring 1. So this time we want to go back to Earth, which make sure you're on Earth. We want to set the friction to 0, like we have in all our other experiments. We don't really need to show the energy graph, so we can neglect that. We're in real time like we always have been. We've got the stopwatch going, or the stopwatch up, so we can use that. Now we just need to grab the yellow mass, which we don't actually know the exact mass of, get that bouncing, start the timer. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, I'm going to turn up the friction and it'll stop bouncing. So we're back on Earth. We use the yellow mass, and our count for 30 bounces or 30 periods was 23:61, or 23 seconds and 61 hundredths. So now I'm going to take that 23.61 61 divided by 30 on my calculator, and I get 0.787 for the time for one period. Oops, that should be in the yellow box because we were using the yellow mass. Good thing I got that. So the spring constant we found in table 1, if you scroll up in your lab, we worked on that together in part 1. We found the spring constant for spring 1 in table 1 was 10.11. So we can use that value for all 3 calculations here. We're going to use this formula now that we know the period and we have the spring constant, we have K, we have T, we know what 2 pi is. So we can now figure out the mass of the yellow mass. We don't know the exact number. So let's go figure that out. So here's how we calculate the mass for the yellow object that we just found the period for. So here's the equation that I took from the lab sheet. Mass equals K times T divided by 2 pi squared. We know K, the spring constant, we got that from the table. We also know the period, T here, so we can put that in, 0.787. We know what pi is. In fact, a lot of scientific calculators have pi in there, and so that's going to equal the mass. So we simply have to do a little bit of math here. So take 0.087 and divide it by 2 times pi on your calculator. So when I took 7.87 on my calculator and divided by 2 pi, I got 0.105. I rounded it to the 3 numbers since we only had 3 numbers here. Now I need to square this. So if you don't have a scientific calculator, just go 0.105 times 0.105, or if you have a fancy scientific calculator, you can square it and then multiply by 10.008. When I square it, I get 0.000120. And then I'm going to multiply that by the spring constant, which is 10.88. So when I do that, I get 0.00131, and that answer is going to be in kilograms. Okay, so my earlier answer was like 1 something grams, and that looked kind of weird. So I went through and I did find a mistake right here. Instead of 105, it was 1.25. So when I squared that, I got this. And when I multiplied that times 10.88, I got 0.71 kilograms, which is about 171 grams. Equals 171 grams. If you just multiply by 1,000, because there are 1,000 grams in a kilogram, and that seems about right. The yellow mass is bigger than the green one, but smaller than the red one, so we know it's kind of the middle one, and that's a reasonable answer. So I'm going to put 171 grams as my answer, and here is, you can use the rest of this math. Just substitute in the different T for the green and the red mass and solve using the same procedure. So use a different T, but you'll use the same K because the spring constant of a spring doesn't change based on the math or the mass you hang on it. So we found the answer for the yellow mass here using our calculations that we just did. Now it's your job to go count the period for 30 bounces, and then divide by 30 to get the period for green, and go put it into the formula like we just did. And then do the same thing, go back in and count 30 bounces for red, divide by 30, get the T, and then put it into the formula like we just did, and figure out the mass for the red object. So stop the video and go do the green object and the red object and find the mass. Now that you're back, let's talk about table 7. This is where you get to mess with the spring constant. Look at the different softness or hardnesses of the spring, or how hard it is to distort the spring. So we want to hang a 100-gram mass from spring 3, because that's the one where you can change the spring constant, to find its period of motion as the spring constant is changed. So you can draw the softness gauge here. This is the softness gauge, a screenshot from the simulation, or you can just do a little mini screenshot here and stick it in the table if you would rather do that. So for right now, I'm just going to do soft. So we know that it's all the way to the left. Let's go to the simulation and count 30 bounces for a very, very soft spring 3. Hello, we're in the simulation here. Here's spring 3. Before we proceed, we want to make sure that we're in Earth's gravity. Since all of the other calculations, we've had friction as 0. Let's check friction to none. Let's set the softness of spring 3 all the way over to the soft side. Let's hang a 100-gram mass, get it bouncing, and then we'll start counting 30 bounces and time that. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Wow, that took a long time. So maybe you noticed something about how far the spring is displacing itself. Here, let's turn friction up here to stop the spring. Eventually, some of that energy that's kinetic will be converted to heat, and the heat will dissipate, so the energy will leave the spring system and it will slow down and stop. So 4138 is the number we want to transfer to our lab. So we've got 41 seconds and 38 hundredths. I divided that by 30 on my calculator, and I get 1.37 seconds, which is a lot different than some of the periods we found earlier in the lab. So now it's your job to set the softness to medium, maybe hard, whatever you want. Just make sure that you let me know where that gauge was. Remember to reset the friction back to none when you go back and check 2 other different spring constants that you choose. So that's what you do for table 7. In part 4, you get to work on this part on your own. The spring constant of spring number 1 we found out in table 1. We used a formula, and you're going to have to put that formula here. You'll have to go find it. It's around table 1. And look at how the spring constant affects the elastic potential. The elastic potential of a spring is when you pull down on the spring, the fact that it bounces back up. It has some stored energy in the spring that you've stored in the spring by pulling it down or distorting it or distending it. And that potential energy is converted into kinetic energy when the spring snaps back up. So how does the spring constant, the K, affect that elastic potential energy, that springing back up of the spring. How does the spring constant affect the kinetic energy of the spring? So you might want to use the slider to change the spring constant for spring 3 and play around a little bit to find the answer to that one. You can find the gravitational acceleration on Jupiter or on the moon using some of what we figured out. Using what you know about gravitational force from Lab 504, why do the moon and Jupiter have different gravitational accelerations? Think about that. What do you know about the universal gravitation constant, and what numbers factor in, or what variables factor into that formula? Remember, m1 times m2 divided by r squared. What's going to be different between Jupiter and the Earth in terms of that universal gravitation constant, or that universal gravitational formula? So these you can use that Hooke's law. 8, you can use Hooke's law to figure out. You're looking at the distance the spring's going to be extended, or the displacement. That's x in our formula. And how much force, that's the F in our formula. Remember, the formula for Hooke's law is F equals the spring constant, K, times the displacement, or how far the spring is stretched. So there's a handy formula for you. If the spring stretched 20.2 meters when a 200-gram mass was hung from it, what is the spring's spring constant? Well, you can find the force from using gravity, 9.8 meters per second on Earth, times the kilograms here, which would be 0.2. Let's make this 0.2 kilograms. And figure out the force. You've got the displacement, so then you can rearrange the formula. K is equal to F divided by X. Press return. Oops. So you can use that formula to figure out the answer. The periodic motion of the spring we just discussed. So write down the masses of those different unknowns in the simulation. Highlight increase, decrease, or remains the same for 14, 15, and 16. Amplitude is the displacement, or how far the spring stretches. Does the amplitude of a spring's movement depend on the period? And here's a little thinking question. And when you're all done answering all the questions, put the assignment in the assignments area under Lab 5.06. Thanks so much, scientists. We'll see you again for Lab 5.10.